Okay, so in this video, I'd like to go over hybridization and more importantly, just the fundamentals to resonance and how it pertains to hybridization. In further videos, we will move forward from these concepts, but I want to start with the beginning. So in general chemistry, you go over hybridization theory, you kind of learn about the D block, the S block, the P block, the F block, and so on. In organic chemistry, we stick mostly to the top right of our periodic table. We're looking at the P block, and that by default incorporates the S block as well. And so when we're thinking about hybridization, we're thinking about atoms and their S and P orbitals, fusing these orbitals together, so to speak, or hybridizing them when they form bonds. And then you result in sp, sp2, and sp3 orbitals. Now what we're really talking about is that we have highly positive and dense nuclei. They have these tiny negative electrons flying around them. And in chemistry, to understand things in a chemical sense, you really are focusing on the energy of those electrons. And these orbitals are chemical speak for the energy and how we represent them and simplify the discussion about the energy of these electrons. Okay, so we're thinking about the environment of these electrons. We're thinking about what is around them, how many dense positive nuclei are around them, and therefore what is their energy, what is their trajectory, how do they move around these atoms and therefore these molecules, and how does that affect the molecules chemically, how do they react. Okay, we do want to point out the importance of the octet rule. That's just saying we should have 8 electrons around any given atom. There are some exceptions. The main one for organic chemistry is you only have 2 electrons around any given hydrogen. That's all. That meets its capacity. Otherwise, it's 8. Okay? And hugely important with understanding hybridization, determining which of the 3 options we have between sp, sp2, and sp3 atoms is knowing if their electrons are localized or delocalized. That's really asking, do they move? Can they resonate? And then we also incorporate pi bonds. When we understand if they're localized or not, we can then understand, like I said, sp, sp2, or sp3 hybridization. From there, we can lead to bond length, at least in a relative sense. We could also talk about the geometry, the shape of these molecules. We can talk about using electronegativity. From geometry, we can lead into the polarity of a given atom, which talks about its intramolecular forces. Also from the geometry, we could lead to the 3D model, which is just another way to represent and further understand a given molecule. So we want to focus on resonance first. Resonance really paints the picture, begins the discussion about hybridization and what we're working with. And you're looking at each individual atom of a molecule at a time with regard to understanding its hybridization. Okay, so there's an sp2 or an sp3 or some label that applies to each individual atom of a molecule. And to, like I said, begin that conversation, we're looking at resonance first. Now there are 2 very basic, so to speak, resonance examples that I want to just show and set aside in the beginning. So we have the first one, any benzene ring or a phenyl functional group. They both look like this. These electrons can rotate around the ring, and they essentially are spiraling all the way around, but they can rotate and it's considered resonance. Okay, we also have open shell atoms. This is referring back to the octet rule. So we see this iron, the Fe, has 2, 4, 6 electrons around it, and thus has an open shell. It does not have 8. And therefore, the chlorine can push a pair of electrons down. Let me show that. Can push a pair down, and thus make a full octet for the iron. We get some unfavorable charges, but we have a full octet. So it is a possible form of resonance, and it does have some energetic favorability at times when it comes to providing a full octet, although we have unfavorable charges. Okay, the meat and potatoes of hybridization is understanding the electron sharing in a molecule. Spreading electrons are out among many different atoms, and this has really 3 very generic looking models is what I want to show here. So we use A as just a position holder. It can be any atom in theory, and it really just needs to have at least one lone pair of electrons. One lone pair, and then either a single or double bond to the adjacent atom. Here I'm using carbon consistently, but it does not need to be a carbon. It can be theoretically any atom. And the A position to the adjacent atom can have either a single or a double bond. And then one of the next adjacent interactions or bonds can be either a double or a triple. Okay. The central atom typically can only have 4 total bonds around it, or 8 electrons, right? So we tend to have something that looks like one of the 3 shown here. Okay. Stick to the rules. Stick to these rules, memorize these, and know their applications, and that will be the quickest way to understand this material. Okay. And the 3 rules, to reiterate, are: we need a lone pair at the A position. We need a single or double bond between A and the next atom. And then from that next atom, here consistently carbon, we need that carbon to have a double bond or a triple bond with another adjacent atom. Okay, here I'm using oxygen consistently. Okay. Down here, I have some examples. We show the actual resonance. So it's always going to be what I like to consider or think about as just moving or pushing or bouncing electrons through a molecule. And you can do this several times over, but these are showing just one bounce. And it pushes them up to the oxygen, and then we have a charge change. Okay, so I'll draw in these additional electrons that were forgotten and show the relative increase in positivity when you push electrons away from the atom, and a increase in positivity when you push them up to an atom. We see the same thing over and over. The electrons come down, increasing the number of bonds between the A position and the adjacent atom, here carbon, and we always end up pushing either the double or triple. We push one of them up, and we always have a charge change. So here we went from neutral, and it's just an increase in positivity or a decrease in negativity depending on what we have going on. And just the opposite, when we're adding electrons to an atom, it goes from partially positive or a positive formal charge on this Lewis structure, and it becomes neutral, or 1 increment increase in negativity, 1 increment decrease in positivity by gaining one lone pair. Okay. Last example, last generic example. We see the same trend, just pushing electrons. And here, once again, forgot formal charge, but it's all the same. To the right here, I have some examples. We have, carboxylic acid, showing that, this is the A position here. This is our A position. And we see that it can have other bonds. That's okay. It can be neutral. It can have a formal charge at times. We could have started at any of these molecules on the right and gone to the left just as easily as we're going from left to right. Okay, and it's important to point out that all Lewis structures are representing one molecule. Okay, so any and all Lewis structures that you can draw are indicative of the characteristics of the molecule. So we could look at this structure here, and we would have to recognize that this oxygen does have some partial negative charge, even without drawing or looking directly at this molecule here. Okay, and we would know that this oxygen has some partial positive charge. Another note on charges is that the net charge, the total charge, if you add them all up in the given molecule, needs to be consistent. So here we have +1, here we have +1, +1, -1 equals, again, +1. Last example, kind of consistent with the ones to the left of them. So we have carbon dioxide, CO2. Okay, we get our bounce of electrons, and so you have it. The essence of this video, the point that we're trying to make here is, can the electrons move? They need to fall into one of these 3 categories we're very focused on the third category here, but we're saying, can the electrons move? And to answer that question, we really resort back to our three rules here. Do we have, looking at a given atom and positioning it at the A position, does it have a single or double bond to an adjacent atom? And does that atom have a double or triple bond to its next adjacent atom? And does the A position have a lone pair? If so, we satisfy the criteria to allow for resonance. And we say, okay, one of these lone pairs on the A position can resonate.